Okay, couple things. So looking at the board, I see all questions that are first order linear differential equations, which we'll certainly get to today, but it's not where I want to start. I will also point out, just because I don't want you guys to waste your time writing from beginning to right. This question here, for y prime minus y equals b to the t over 9. And this question here, 2y prime minus y equals b to the t over 5 are virtually the same. Right, the only difference is you got a 4 here, you got a 2 here, you got a 1/5 here, you got a 1/9 here. You really don't write them. Like just, we're only gonna do one, because they're, and if you look at the rest of it, they're both the same stuff after. So if you see yourself asking a question that's essentially already been asked, then the constants don't really matter that much. I mean, they matter, but like, just be aware, like, you don't need to duplicate that work. And then there was something else I wanted to mention. I'm trying to remember what it was. Oh, I know what it is. Today is the 4th, which means next Monday is the 11th, and we don't have class, right? Veterans Day, no classes meet next Monday. So don't come to school next Monday. We won't be here. Holiday for everybody. Don't come to class, relax, enjoy a 3-day weekend finally. Yeah. All right. So before we start doing that, let's do a couple other differential equations. Where were you guys? Sorry, there we go. Yeah. So let's look at something like we want to solve x squared plus 4 times y prime equal to x times y. And so when we get to the place of solving differential equations, there are two things you should ask yourself when you're solving a differential equation. Sorry, let me move this out of the way. It's terrible. I said two things and I'm hesitating to find the second thing. Oh, no, not two things. Sorry. There are two ways we can solve them. And in this class, there's only two. You have one of two options. One option is it's separable. Separate y's on one side, or dependent variable on one side, independent variable on the other side, and then integrate both sides, which is what this one's going to be. Or the other option is that kind of stuff. First order linear differential equation, which we'll get to later. The second thing I wanted to point out was that when you're solving a differential equation, we are trying to find a function, right? So the solution here is going to be some y as a function of x. That's always what we're looking for when we're trying to solve a differential equation. And I don't have any good. Okay, cool. So let's solve it. So if you're thinking, even if you're not thinking separation of variables, it's almost always better to write the derivative in the Leibniz notation, meaning I should really write this as x squared plus 4 times dy dx equal to x times y. So then I can easily see that I want my y's to be on the left side because dy is on top on the left. I want my x's to be on the right side so that when I multiply sides by dx, dx isn't in the bottom, right? We don't want our differentials, dx or dy, to be anywhere other than the top or not in the denominator. So I'm going to multiply both sides by dx. I might as well also divide both sides by x squared over 4. So I have dy equal to x divided by x squared plus 4, multiply by dx, and then just try not to write all the things. I'm also going to divide both sides by y. So 1 over y, James. So now I've separated my variables. All the y's are on the left, all the x's are on the right, and then we integrate both sides. So the integral of 1 over y dy equals the integral of x over x squared plus 4 dx. Here's where why part of the reason we've been practicing integrating things is so that we can actually solve this. The antiderivative 1 over y is the natural log of, do I really care about the absolute value? I know I say I don't, and I just say don't. Yeah, I'm going to try not to care about the absolute value and just say it's the natural log of y. Over on the right-hand side, we do have to use u substitution here. So we can see that we let u equal x squared plus 4. Our du is 2x times dx. So 1/2 du is equal to x times dx. And the integral is going to be the integral of 1/2 du over u, which is going to be 1/2 natural log of u, which is 1/2 natural log of x squared plus 4. That's what we're going to get over here. 1/2 natural log of x squared plus 4 plus c. It is important as a plus c. You don't need to put it on both sides, and you should typically put it on the side where the independent variable lives. If we're trying to solve for y, it doesn't make sense to have the plus c over here and then move it over there. And if you, yeah. So then solving for y, we're going to get e to the natural log of y equal to e to the all this. 1/2 natural log of x squared plus 4 plus c. So we're going to get y equal to, okay, a couple things we should do here. Technically, this is a fine answer, but it doesn't look great. Sorry, let me do this real quick here. So there's two simplifications we can and should make. One of them is breaking it up as e to the 1/2 natural log of x squared plus 4 times e to the c. And then I'm always a fan of calling e to the c a new constant. I typically choose the letter A. All right, in front, and then e to the 1/2 natural log of x squared plus 4, that 1/2 power can come up as, sorry, that 1/2 coefficient can come up as the power of x squared plus 4. And so we can write that as just e to the natural log of x squared plus 4 to the 1/2, which is just x squared plus 4 to the 1/2 power. And without any initial condition, that's all we've got. Oh, sorry, yeah, apologies, yes. Without any initial condition, your solution is some constant times the square root of x squared plus 4. And not that you ever should need to check, but if we needed to check, we could take the derivative of that, plug it in there, take the original function, plug it in there, multiply out both sides, and see that they are indeed actually equal to each other. Yeah. Correct. Some people just replace it with C. For some reason, capital A feels like it should be what I like to call it, but anything you like is fine. But yeah, typically constant, sign constant, just a new constant. If we add a constant to a constant, we just call it a new constant. So we're trying not to write more than we need to. Yeah, let's do this next one, and then we'll move on to some good old first order linear differential equations. Mouthful. So let's look at this next one where we have y prime equal to x times y times sine of x divided by y plus 1. And we're given the initial condition that y of 0 equals 1. So when you see an initial condition, you should think to yourself, oh, that means I'm going to have to solve for my constant. That's what the initial condition means for us. It means solve for the constant. I wish I could think of a good word that started with I that was like solve for, because C starts with, right? Investigate the constant. How about that? Initial condition, investigate the constant. Find the constant. After you've done all the other work. All right, this is looking pretty separable to me. I can see that I have dy dx on the left. And I could even break this apart as x times sine of x times y over y plus 1, just to really see that it is a function of x multiplied by a function of y. Great. Bring all the, I'm usually writing my derivative on the left side. It doesn't really matter, but bring all the top variables to the left, all the bottom variables to the right. So I'm going to bring my y's to the left. So I'm going to multiply by y plus 1. I'm going to divide by y times dy. On the right-hand side, I have x times sine of x times dx. We've separated the variables. Now we anti-differentiate. If I heard someone trying to ask a question. Two things I would do here. One, y plus 1 over y, we should just divide each thing by y. So we should really write this as the integral of 1 plus 1 over y. And the right-hand side, the integral of x times sine of x dx. Left-hand side is a straight shot. We get y plus the natural log of y. Right-hand side is integration by parts. So we're going to let u equal x, dv equals sine of x dx, du is 1 dx, v is the antiderivative of sine of x, which is negative cosine of x. So we're going to end up getting, let's see, u times v, so negative x times cosine of x, minus the integral of v du, so minus the integral of negative cosine times dx, but a minus is a plus. the interval of cosine of x dx. So we have y plus the natural log of y equals negative x cosine of x plus the antiderivative cosine is sine of x plus c. I have some bad news. We can't solve for y here. This can't be done. Like literally, we cannot. Not just like we can't, but nobody could. Y can't be solved for in this case. So we're going to leave it as is, but we still have to find the constant c. So to solve for c, we're going to plug in 0 for x and 1 for y. So we get 1 plus the natural log of 1 equals negative 0 times, it doesn't really matter, plus sine of 0, which is also 0, plus c. So we get 1 equals c. So our final solution, which feels a little disappointing, but it is what we've got, is that we have our, y plus natural log of y equals negative x cosine of x plus sine of x plus 1. Yeah. Sometimes that happens. Sometimes you get an equation where you can't actually isolate y, and that's just the way it goes sometimes. Yeah. Cool. Questions about that one? All right, let's look at the ones on the board. Actually, let's not just yet. Let's talk about the general idea here. So, yeah. First order linear differential equations, bless you, which we are going to abbreviate because it's too much to write. Often abbreviated as FOLD. So when you're trying to see, so this is the other method, right? It's either going to be separable or it's going to be this if you're asked to solve it. Just want to clarify, right? There could be other differential equations you're faced with where you might be asked to like verify something's a solution. Those could be anything. But if you're asked to solve a differential equation, we only have the methods available to us to either solve separable ones or to solve first order linear. So here's the standard format. The standard format is going to be something like y prime plus p of x or p of t, depending on whatever variable is our independent variable, times y equals q of x. Or it could be y prime plus p of t times y equals q of t, right? It doesn't matter if your independent variable is x or t or some other letter. So this is your standard format, and there's a very, very, very standard process for solving these differential equations. Yeah, let's do it the long way. So normally what I would do is go straight to finding what we call the integrating factor. But some people, specifically I think Burke, likes to show that what we're doing is we're trying to multiply this whole equation by something so that we get something special happening. And something special is always going to be the same thing. So I'll talk about that when we get there. But the idea is we're going to multiply this whole equation by something so that it looks like the left-hand side is nice to deal with. I know that's vague. We'll get that in a minute. Typical names for the integrating factor. So the integrating factor, people either call it mu of your variable or capital I of your variable. I prefer mu because it's the right way, but I is a perfectly fine choice. I think has everybody words? Is there any class that hasn't talked about integrating factors yet, or first order linear differential equations yet? Okay, great. For the classes that have talked about it, who's used I? I know somebody has. I've seen it. Who's used mu? Okay, great. So it's not, if it was all I's, I would use I, but since it's some mu's and some I's, I will pick what I like, which is mu. But really, I'll probably go back in different problems. So here's the idea. We're going to multiply the whole equation by the integrating factor. So multiply by mu of x. So we're going to get, I want to write this out very specifically, mu of x times y prime plus mu of x times p of x times y equal to mu of x times q of x. Here's what we want to happen, which is going to happen every time. We want the left-hand side to look like we took the derivative of a product. So I want to point out that if I took the derivative of mu of x times y, where y is also a function of x, we're just being lazy and not writing y of x, using the product rule, and yeah, here's what we get. We would get mu of x times y prime plus mu prime of x times y. And notice that that is almost exactly what our left-hand side is. We've got a mu of x here, we've got a mu of x here. We've got times y prime here, times y prime there. We've got times y there, and the only thing that we need to reconcile is that mu of x times p of x better equal mu prime of x. And that's not too hard to make happen using separation of variables. Here's what we need. We need mu prime of x to equal mu of x times p of x. Or using the Leibniz notation, d mu dx equal to mu of x times p of x. So I want to point out that I'm just going to think of mu of x as just being mu, right? Like it's not, there isn't an x there. I kind of did myself a disservice. I should have written it as just mu times p of x. It doesn't really matter, but so then we're going to separate. We're going to bring the mu's to the left, the x's to the right. So we're going to have 1 over mu times d mu equal to p of x. We're going to integrate both sides. So the integral of 1 over mu d mu is equal to integral of p of x dx. Integrating 1 over mu, we get the natural log of mu equal to still the integral of p of x. That integral is not going away. And finally, solving for mu, we get that mu of x is equal to e to the integral of p of x dx. Oh, thank you, yes. I want to point out, I didn't use any specific functions here. I just called them names, mu of x, p of x, q of x. And regardless of what they're called, the integrating factor is e to the integral of p of x. End of story. Well, not end of story, but like end of that part of the story. So whenever you're trying to find the integrating factor, that is always how to find it. It is e to the antiderivative of whatever is being multiplied by y right here. Okay. I want to point out also that if you took the derivative of mu of x, mu prime of x, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So in this case, the derivative of e to the integral of p of x is e to the integral of p of x times the derivative of the integral of p of x, which is the derivative of the antiderivative of p of x, which is p of x. Hey, look, mu prime of x is exactly equal to mu of x times p of x, exactly as desired. All that to say, you probably don't have to do all that work. It's good to see it. It's good to know where things are coming from. But in reality, if you're actually solving a first order linear differential equation like this, you're going to find mu of x and then move along. So after you multiply by mu of x, here's what you actually want to do next. You want to rewrite this left-hand side as the derivative of a product. Mu of x times y. So what we're going to do now is we're going to take this equation, say, great, we have mu of x times y prime equal to mu of x times q of x. We're trying to solve for y, right? The goal for a differential equation is always to solve for the function if we're being asked to solve for it. So to get y by itself, I have to undo this derivative. How do we undo a derivative? With an antiderivative. So anti-differentiate both sides. Don't actually write the antiderivative of the derivative. Just write down that you get what's left. Although you could write down the antiderivative here. That'd be fine. But on the right-hand side, it is the antiderivative of mu of x times q of x. Finally, actually integrate this and then divide both sides by mu of x. So your final result here is going to be that your y, or your y as a function of x, is 1 over mu of x times whatever you got when you integrated the product of mu of x times q of x. And don't be a fool like I was when I took this class many years ago, or not this class, but the class where I learned about differential equations. Don't think you can cancel those mu of x's. They do not cancel. They might cancel somewhat after you have integrated mu times q, but you have to multiply these together and then do the antiderivative, and then after you've done that, divide by mu of x. I should point out, some people are totally fine with you just memorizing this final result. I don't imagine that's Piranha for sure. Like she is not cool with that 100%. I don't know about Cooper Jacob. I don't know about Challenor, right? Challenor's the other guy. John Challenor, right? Is there anyone in Challenor's class? Yeah, cool. They probably all care, but I don't know how much they care. So you should get clarification from them on exactly what work they want to see when you are solving a first order linear differential equation. Okay, let's actually do an example now. Let's look at that. Which one do I want to start with? Sure, let's do the one that's on top, for lack of a better word. Actually, let's do the second one. I see why. Yeah, let's do this one. So let's look at solving y prime minus 8y equal to 7 times sine of t. And they've told us annoyingly that the initial condition is y of 0 equals y naught. Why not? Okay. So this one's already written in the standard format, meaning y prime is by itself. You've got some function of your variable times y, not a very interesting function times y, but still something times y, equal to some other function of t. So this is where it's easy to make a mistake. You really want to think of this as y prime plus some function of t, even if it's a constant, times y equal to 7 times sine of t. So it's really, really vital here that, oh man, this one's going to suck. Oh yeah, oh, I gotta start with this one. Okay, I might change gears because this one's awful. We might do it anyway. So I want to point out that this is a function of t, even though there's no t's in it. It's a constant. But the thing that I want to actually make sure we all catch is that you catch the negative sign there. It's really easy to say that your integrating factor is e to the integral of positive 8t. But if there's a minus sign here, that minus sign goes with your p of t function. So here I would say my p of t, not that you have to write this down, is -8, and my q of t is 7 sine of t. Okay, so let's find the integrating factor. So our integrating factor mu of t is e to the integral of -8, which is just e to the -8t. A lot of the times this will simplify into something nicely, like especially if you have an e to the natural log of something, it is in your best interest to simplify your integrating factor as much as possible every time. In this case, it doesn't simplify, so we're just going to multiply the whole thing by mu of t. So now our new equation is going to be e to the -8t times y prime plus e to the -8t times -8 times y equal to e to the -8t times 7 times sine of t. Every time you do this, you should recognize that the left-hand side is the derivative of a product. And the product is always going to be your integrating factor times the function you're trying to solve for. Every time. Because, right, it's your not derivative of this times the derivative of that. Okay, so e to the -8t times y prime, plus then you take the derivative of e to the -8t, and you exactly get e to the -8t times the derivative of -8t times your y left alone. Every time. And here's where it's going to get painful. Yeah, I remember this problem. It's not my favorite, but it's also totally fine. So just integrating both sides, we're going to get e to the -8t times y equal to the integral of e to the -8t times sine of t. I'm going to bring that 7 out in front. Okay, so we're going to do this next part we're going to do as quickly as possible. It's going to be a little bit painful, but we're going to integrate e to the -8t sine of t. This is one of those problems where you have to do integration twice, get the same thing showing up again. and then add it back over, etc. So I'm going to work through this pretty quickly. So we're integrating e to the negative 8t sine of t dt. And I'm going to make, I would literally like, so I'll point out, usually I tell you when you're doing inertia by parts, you should do trig before exponential function as your u. Although technically, if you have an e to the something and a sine or a cosine, you can actually make either choice. I'm going to make the other choice here, letting u equal the e to the thing, because I'd rather multiply by negative 8 than divide by negative 8. And if I make my dv equal e to the negative 8t, I have to divide by negative 8 to make my u e to the negative 8 thing to multiply by. So I'm just going to try to make my life a little easier. So I'm going to say that my u is e to the negative 8t. My dv is sine of t dt. My du is negative 8 e to the negative 8t dt. My v is the antiderivative of sine, which is negative cosine of t. Plugging this all in, we get that times that. So negative e to the negative 8t times cosine of t minus the integral of v du. That's a minus times another minus. So it's going to be a minus, minus, minus. So still minus the integral of 8 e to the negative 8t times cosine of t dt. Bringing out the 8. We're going to do another one. We're going to let u equal e to the negative 8t again. dv is cosine of t this time. du is again negative 8 e to the negative 8t. And v is the antiderivative of cosine, which is sine. So we're going to get negative e to the negative 8t times cosine of t minus 8 times my u times v. So e to the negative 8t times sine of t minus the integral of my v du, which is going to be a minus and then another minus, so plus 8 e to the negative 8t sine of t dt. Okay. I'm going to try to do as little as writing possible here. So I've got my original integral equal to negative e to the negative 8t times cosine of t minus 8 times e to the negative 8t times sine of t. Oh, no, that's right. Yeah. Plus, sorry, minus 8 times 8 is minus 64 times the same integral again. Okay, and the next steps we're going to do quickly. I'm going to add this over. I'm going to get 65 times my integral equal to all this right here. And I'm going to divide both sides by 65 to get finally the integral of e to the negative 8t times sine of t dt equal to 1 over 65 times all of that. Negative e to the negative 8t times cosine of t minus 8 e to the negative 8t times sine of t. Good God. Plus c. I'm not going to write plus c right now. The plus c is important though. Okay. So back to the problem we were looking at. That means that here we can say that e to the negative 8t times y is equal to 7 times all that. So 7 over 65 times negative e to the negative 8t times cosine of t minus 8 e to the negative 8t times sine of t plus c. I don't need to have the c multiplied by 7 over 65 because it's still just a constant. But it's really, really important that when I divide both sides by e to the negative 8t, or multiply both sides by e to the positive 8t, which is easier to do, the c also gets divided or multiplied by whatever that integrating factor is. It's really, really vital, actually. So here's what we're going to get for our function y of t. Well, check this out. If I divide everything by e to the negative 8t, that's going to go away, that's going to go away, and I'm going to get c divided by e to the negative 8t, which is c times e to the positive 8t. So my simplified answer is 7 over 65 times negative cosine of t minus 8 sine of t plus c times e to the positive 8t. Gross. Oh, y of 0 is y not. It's stupid. Okay. So fine. I really don't love that part of this problem, but let's get down to the ends here. So finally, let's just write this again, and then we'll figure it out. This isn't a bad problem. It's made so difficult by the unnecessary terrible integral here. So we know that y of 0 equals y naught. So we're going to use that to solve for c. So we're going to say that y naught equals 7 over 65 times negative cosine of 0, which is -1, minus 8 sine of 0, which is -0, plus c e to the 0, which is c. And then finally, we can solve for c and say that c is equal to y naught plus 7 over 65. That seems gross. So then I guess our final answer is y of t equals 7 over 65 times negative cosine of t minus 8 sine of t plus y naught plus 7 over 65 times c e to the 8t. And now for the question you've all been waiting for. What does y naught have to be so that this thing remains finite as t goes to infinity? Well, I'll remind you, cosine and sine are always stuck between -1 and 1. So this whole part doesn't really matter. This part's always going to be finite. What matters is this part over here. E to the 8t, sorry, there shouldn't be a c there, apologies. Let's make that a big parentheses instead. Sorry about that. E to the 8t is going to get larger and larger and larger as t goes on and on and on and on. So the only way for this thing to remain finite is if this coefficient is what? That much. And if it's anything other than 0, this is going to get larger and larger and larger, or negatively larger and larger and larger eventually. So the only way that this thing is finite is that y naught has to be -7 over 65 for y of t to remain finite. Blah. Kind of a lot. It's really a lot. Should have gone with my gut and done the other one first. Oh well, that's life. But that's what that problem is asking you to do. It's asking you to do a whole lot and then be like, oh yeah, this part's going to grow infinitely large, so we need this coefficient to be 0 for it to not grow infinitely large. Well, let's look at the other ones. So the reason I did that problem first was because I wanted to point out that if you have a negative something times y, that negative has to get included in your e to the integral of whatever that thing is. I should have done the other one over there. Oh well. Let's look at the one above it. Let's look at t times y prime plus t plus 2 times y equal to t. Is this a first order linear differential equation? Is it first order? Yes, my highest derivative is the first derivative. Is it linear? So when I ask the question, is it linear, we should only be looking at which letter, t or y. Only one of them matters. You should definitely be looking at y. So whatever your function is, whatever your dependent variable is, that is the one that we care is first order, first derivative, and linear for the first power. No other higher powers. If that was a y squared there, I'd immediately be like, well, we can't do first order linear because it's not linear. Great, it is a first order linear differential equation. I should also point out some first order linear differential equations can also be solved by separating variables, depending on what you've got. I don't think this is one of them. And if it's written already in the kind of format like this, I generally wouldn't try to make it separable because usually they're trying to push you in a direction if they've written it this way. But it's not written in the standard form. So we have to, before we can do anything, we need to write it as y prime plus some function of t times y equal to some other function of t. Typically, that means divide everything by whatever is being multiplied by y prime. So divide everything by t to get y prime plus 1 plus 2 over t times y equal to 1. You cannot move forward without doing it. So now let's find our integrating factor. So the integrating factor, I'm going to call it I of t this time just to change it up. I of t is equal to e to the integral of your p of t, which is 1 plus 2 over t dt. I don't think there's anything wrong with labeling these things, or you could tell me like, hey, there's my p of t, there's my unexciting q of t. totally worthwhile to do that. I'm integrating this, you're gonna get e to the t plus 2 natural log of t. And even though this looks like it might not simplify, it does. And you are definitely encouraged to simplify this to make your life suck less. So this is e to the t times e to the 2 natural log of t, which is e to the t times e to the natural log of t squared, which is just e to the t times t squared, or t squared times e to the t. And that is a much better thing to write and probably to deal with as well. If you simplify this as much as possible, you'll see what cancels more easily later on. All right, so we multiplied the whole thing by an integrating factor. It's going to look kind of gross. So we're going to get t squared e to the t times y prime plus t squared e to the t times 1 plus 2 over t times y equal to t squared e to the t times 1. All right. It should be true, although I'm having a hard time believing. No, I believe it totally. If I distributed the, well, yeah, we'll see. So I should say this next step, after you've done it a few times, should require zero thought. It's always going to be, in fact, here's my trick really. I look at this term here. I rewrite that term and just move where the prime is. It's true. I'll point out, if you're unsure about this here, well, let's actually do it just to check. I do like to check my work occasionally. So if you take the derivative of this, it's going to be, we're going to think of it as t squared e to the t times y prime plus, now we're going to do the derivative of t squared e to the t, which is 2t times e to the t plus t squared times e to the t times y. And if you actually distribute this out, you get a t squared e to the t times 1 plus a 2 times t squared times e to the t divided by t, which is a 2t e to the t. So yeah, it totally works out just fine. You should never actually need to check this because it should always be true. On the other side, we have t squared e to the t. We integrate both sides. We get t squared e to the t times y equal to the integral of t squared e to the t. T, that is times. And then we're going to integrate the right-hand side using integration by parts. Let's use tabular integration. Our u would be t squared. The derivatives are 2t, 2 and 0. Our dv would be e to the t, and all its antiderivatives are also e to the t. How nice, lucky us. So it's plus t squared e to the t minus 2t e to the t plus 2 e to the t. So we have that t squared e to the t times y is equal to t squared e to the t minus 2t e to the t plus 2 e to the t plus c. It's really, really important that plus c gets in there. Because now if I do, good question, James. Sorry, I said good question. Like I asked myself a good question and didn't say that to you all. The good question I'm asking myself here is now the best moment to plug in t equal to 1 and y equal to 6? No, it's not. It might be, but it's not going to kill me to go a step further and solve for y. So y is going to equal, I do like simplifying this. I would write this as, from dividing by t squared e to the t, I'm going to get 1 minus, let's try that again. Let's actually just write this again so it doesn't look crazy when you're trying to see it later on. So dividing both sides by t squared e to the t, I'm going to get y equal to 1 minus 2 over t plus 2 over t squared plus c over t squared e to the t. It's really, really, really vital that the constant term there gets divided by whatever the integrating factor is. Otherwise, the answer is really wrong. And then we can plug in t equal to 1. Ugh, that's terrible, but I guess necessary. And y equal to 6. Ugh, and get 6 equals 1 minus 2 plus c over 1 times e to the 1. Okay, that's less. Could be. So 5 equals C divided by E. So C equals 5E. And then we should go back and find the final. So the final answer we'd have to write into lab work or whatever would be to write that Y or Y of T is equal to 1 minus 2 over T plus 2 over T squared plus 5E over T squared E to the T. You could probably simplify that even more, but I don't care to. If you really wanted to, you could write this as 5 T to the negative second E to the 1 minus T, if you cared to change that up. Okay. So first order linear differential equations, although they are kind of a lot, the process is the same every time. You're writing it in the standard form, you're finding your integrating factor, you're multiplying both sides by it, you're writing the left-hand side as a derivative of a product, you're integrating both sides, you're actually integrating the right-hand side and maybe doing integration by parts or use substitution or maybe partial fractions or something else terrible. But then after you've integrated the right-hand side, then you're dividing by what's on the integrating factor on the left, and then maybe solving for an initial condition, solving for your constant using an initial condition. All right, let's look at that last one over there, and I'll do the one on the left because I don't know. I think I helped someone else with the other one earlier today. They're really the same question. So we've got 2y prime minus y equal to e to the t over 5. And we have an initial condition of y of 0 equals, is that an A? Yeah, that's terrible. Why can't they just give us real numbers? And we're asked to find y and then determine the limiting behavior of the solution as t goes to infinity. Okay, sure. All right, so let's look at the beginning. And even though we're close, we are not written in the standard form. What should I divide the whole thing by? 2. I'm going to write it as y prime. And I do really recommend forcing a plus sign here. I really can't stress, right? Plus, and then, oh, it's going to be negative 1/2 times y equal to 1/2 e to the t over 5. It's going to make it easier for you to remember that your p of t is negative 1/2. And when you find your integrating factor, it's going to be e to the integral of negative 1/2. And that minus sign really does matter. So your integrating factor is e to the negative t over 2. Gross. Okay. So we multiply the whole thing by it. We get e to the negative t over 2 times y prime plus e to the negative t over 2 times its derivative, or should I say the derivative of negative t over 2, which is negative 1/2 times y equal to, did I leave myself enough room here? Barely. 1/2 e to the t over 5, James, times e to the negative t over 2. Okay, barely. Let's do two things at once here. The left-hand side, we're definitely going to write as a derivative. Everybody should write down, everybody should fill this in. What two things go inside there multiply together? And while you do that, I'm going to simplify the right-hand side. The left-hand side should be the derivative of the product, e to the negative t over 2 times y. I'll say again, you can always find it by taking whatever you have multiplied by y prime and just moving the y to the outside of a parentheses that you can fill in for yourself. It always works. I'll say it again, it always works. It's kind of a cool little fast trick, I think. All right, the rest, we've been here before. Integrate both sides, you get e to the negative t over 2 times y equal to the antiderivative of 1/2 e to the negative 3t over 10. Yes, I simplified the right-hand side, and e to the t over 5 times e to the negative t over 2. We're just adding those powers together and getting 2t over 10 minus 5t over 10, which is negative 3t over 10. The good news here is that that function is something we know how to anti-differentiate without doing integration by parts or u sub or whatever. We can just say, great, this is going to be e to the negative t over 2 times y equal to 1/2 times e to the negative 3t over 10 divided by negative 3/10 or multiplied by negative 10/3 plus c. Divide both sides by your e to the negative t over 2 or multiply both sides by e to the positive t over 2, which I think is the better choice if you're dividing by e to a negative thing. So you need y equal to 1/2 times e to, I should have been smarter and multiplied the 1/2 times the -10/3 and got -5/3. Sorry, it's a little gross there. And then -3t over 10 plus t over 2. Well, that should give me back t over 5. Right, -3 plus 5/10 is 2/10, which is 1/5. And then finally, you also have c times e to the t over 2. Interesting. Interesting. And that's our general solution. Right? I feel like I have to double check here and make sure I didn't make a stupid mistake. No, that seems right. I don't feel like I've done anything dumb. Oh yeah, okay, cool. All right. So now we should read the question. Determining the limiting behavior of the solution as t goes to infinity. This behavior depends on the initial value a. Let a not be the value of a at which the transition from one type of behavior to another occurs. Find a naught. Okay. Yay. Okay. So if y of 0 equals a, we're going to say that a, let's use another piece of paper, Jane. So we have y equal to -5/3 e to the t over 5 plus c e to the t over 2. I feel like I'm worried. Here's why I guess that's fine. Okay, sure. So plugging in a for y and 0 for t, I get that c equals a plus 5/3. So I can rewrite this as y equal to -5/3 e to the t over 5 plus a plus 5/3 e to the t over 2. Don't love this. Okay, so here's what I'm seeing. As t goes to infinity, one of these two things is going to overpower the other one. The one that's raised to the power that's like the bigger multiple of t. And 1/2 is bigger than 1/5. So this is the dominating term, as long as this coefficient is, I guess, positive. So here's what I would say. As long as a plus 5/3 is greater than 0, then this term is going to go to positive infinity, and that positive infinity is going to overpower this negative infinity because the exponent is getting bigger faster. Here's an easier way to see that. I got enough time. I might have done myself a disservice by simplifying this e to the t over 5. It might be nicer to look at this as, no, I'm fine. Here's a way to make, I think, this look a little bit easier to parse. I'm going to factor out the smaller power of t. So I'm left with -5/3 times e to the 0 plus a plus 5/3 times e to the 5/10 minus 2/10 is 3/10 times t. So now I believe it's easier to see that, oh yeah, if this is positive, then this whole thing is going to go to positive infinity, -5/3, times this other thing, which is also going to infinity. So if this is positive, then both e to the t over 5 goes to infinity, of course. And the other factor, -5/3 plus a plus 5/3 times e to the 3/10 t also goes to infinity. And infinity times infinity is infinity. On the other hand, if that quantity there is negative, then we still have e to the t over 5 going to infinity because it's just e to the t over 5. But this part here is now -5/3 plus a negative number times e going to infinity. So that other part is going to go to negative infinity. And positive infinity times negative infinity is negative. So I think that's what they're looking for there, but it's a little funky, I'm not going to lie. All right. I've talked all I can talk. It's 2 o'clock. I'm in the usual places at the usual times. We can definitely talk more about this on Wednesday. Yeah. And then I'll say it again, no class on Monday. It's Veterans Day. Also, I posted an announcement about Co-17C next quarter. So if you're planning on taking 17C, there is a co-class. I think it meets Monday, Wednesday, Friday from 2 to 3, but you should double check that. It's on there. It's also the last class you should sign up for, right? We'll get you in if you need to get in. Sign up for your other classes first.